Thanks for the introduction. I would like to first thank the organizers for inviting me to this nice, pleasant place. And I enjoyed the wine a lot. So today I'm telling you about a work I've done in collaboration with Yaroslav at UCLA about magnetic noise and quantum materials. The idea is in general, but I will present some specific model in the talk. Okay, so one important theme of our field is to explore transport of charge-neutral degrees of freedom. In addition to spin, many newly discovered quantum materials provide with other promising options. For example, this valley degrees of freedom in semiconductors and volatile metals. And this talk, I will introduce you to magnetic noise spectroscopy as a potentially very useful probe of exotic degrees of transport, exotic transport degrees of freedom in quantum materials. And I will show you some results for a specific model of a magnetic volatile semimetal, where you have three different flavors, charge, spin, and value transport present. And the punchline is these 3 degrees of freedom can have very distinct spectral characters in a magnetic noise measurement, so it's possible to distinguish their contributions. And with this, we would like to promote the general idea that magnetic noise spectroscopy can be useful for exotic degrees of freedom transport measurement. Okay, so very crudely speaking, to have long-range transport, we would like to have some conserved quantity, and charge or electron number is 1. And when you have rotational symmetry, angular momentum is conserved. And the most ideal typical case, you have spin superfluidity, where spin is good for long-range transport. The situation is not so bad either if the symmetry is slightly broken, because in real lattice systems, almost all continuous symmetry is approximate anyway. Essentially, what we want is a large diffusion length, as in the K length by our last speaker. Okay, so there's also valley degrees of freedom. I'm showing here just the band structure of graphene. So this is a degree of freedom that's protected by band topology. So it's very stable against the small tuning of the band parameters. And in graphene, you have 2 inequivalent valleys, K and K prime, and they essentially behave like a spin 1/2. And as progress is made to study very complex electronic band structures, valley degrees of freedom are also discovered in volatile metals. So this first predicted with band structure calculations and later found in many real materials. Okay, so one way to get a volatile metal is by breaking time reversal symmetry. As here, you have band touching between 2 degenerate bands, and with exchange field magnetic interaction, they can split, and you get 2 Weyl nodes with Weyl valleys with opposite chiralities. In this way, in this situation, the Weyl cones are separated by a small distance near the center of the Brillouin zone. And this magnetic Weyl case is particularly interesting for us for several reasons. To name a few, first, it allows a single pair of valleys, so this is nice and clean to study valley transport. And because you have both valley and spin, there are more knobs to tune for application purposes. And as we heard from previous talks in this workshop, there can be magnetic textures, and there will be this interesting interplay between real and momentum space topologies. Going to transport, we've seen that this non-local geometry is very useful to detect charge-neutral transport. And so in this paper, the authors propose this geometry to study chiral anomaly, actually, by using the property that diffusively driven valley degree of freedom can survive in a long distance. But as we've just seen from the last talk, this is also used to study spin diffusion. And when you have both spin and valley diffusion, it is a question how to separate these different contributions. Here, magnetic noise spectroscopy might be a solution for this. Of course, the method itself is very broad. Today, I'm focusing on a brief introduction to the single qubit relaxometry with NV centers. You can think of NV center as just a single qubit system that is very sensitive to magnetic field due to this Zeeman splitting of its energy levels. And so it's very commonly used for magnetic imaging to detect, to detect stray fields. And sorry. No, it's okay. It's okay. Yeah, excuse me. Okay, so it does not only detect a magnetic field, but also fluctuations of a magnetic field. Thank you. Because when you have fluctuating magnetic field around the NV center, it will introduce a transition between its energy levels. And this transition rate or relaxation rate, when it's coming from high energy to low energy, is largely affected by the fluctuation of magnetic field at the position of the NV center. And when this magnetic field fluctuation is provided by some excitation dynamics in the material nearby, this is essentially probing the dynamic susceptibility like other transport experiments. In terms of probing magnetic field fluctuation, the sensitivity to a magnetic field means we have a high frequency resolution. Yes? I'll get to it in the next slide. Right, yeah. Yes. Frequency resolutions. Dynamic susceptibility in the momentum and the frequency space, right? Because you can control this Zeeman splitting by a magnetic field, and then you can control the frequency that this NV is probing. And so there are two parameters here. One is frequency, and the other is the distance between the NV center to the material. And because this geometric factor, so NV is most sensitive to the dynamics happening at the length scale that's inversely, that's proportional to the distance between NV and the material. So you can actually tune different regimes you want to probe. If the NV is very far away from the material, we'll see, for example, electrons scattered by many times. Then this is the diffusive type of situation. But if it's close enough, it won't see the electron getting scattered, and then it's a ballistic situation. And last but not least, this NV technique is non-invasive, so you don't have to deal with problematic interfacial. Yes.
Is it correct to say that this length scale essentially integration of it is?
Yeah, it's provided by the magnetostatic current. Yes.
Yeah, I think this is a very interesting discussion because of the issue of the topological magnon surfacing. Maybe this technique.
Yeah.
So I'm interested. But this omega, so you measure the kind of frequency spectrum of the noise. And then at some fixed frequency omega of that spectrum, you can get information about the susceptibility of that frequency.
Yes. For example, if you have resonance between MV and magnetic bands, you can pick up the magnetic band.
You can kind of go through the Q space by changing the distance
Yes,
between the
yes,
samples.
exactly. Yeah. I'm going to give a few examples. So anything that, yes?
What's like the number of frequency?
Right. Thank you for pointing this. So the intrinsic ESR frequency is in gigahertz, so it's a low frequency measurement. So anything that provides a magnetic field fluctuation can be picked up. So, for example, you have a charge fluctuation. In this experiment, they probe the charge current fluctuation in silver, and also spin fluctuation, of course, because spin generates magnetic field. I'm showing here an experiment measurement by Chunhui Du's group in UCSD on an antiferromagnetic insulator hematite. And by fitting the relationship between relaxation rate and the frequency of NV with this diffusion model, we can actually get the intrinsic spin diffusion constant and spin conductivity, etc. And it's inconsistent with previous measurement and with this non-local geometry. Okay, so we've seen that charge can contribute and spin can contribute to magnetic field fluctuation. So what about Weyl degrees of freedom? By taking this very simple four-band model, okay, here tau and sigma are polymatrices for Weyl and spin, respectively, and the value cones are there because of finite magnetization that breaks time reversal symmetry. And the charge current is simple. You just sum up the current located at the two valley cones, and the valley current is weighed by weighed by the chirality of the cones. So it's actually a subtraction between the two cones. And from this Hamiltonian, it's very clear for this model, the valley current is directly proportional to the itinerant spin density averaged locally. And we know spin density can generate magnetic field. So naturally, here the valley current couples to magnetic field, and its dynamics will generate magnetic field fluctuations and magnetic noise. So this is why we have three flavors for magnetic noise from this magnetic Weyl system. And here I will, so we treat these three flavors with a very simple but consistent method for their comparison. And it's this Langevin method. So I will explain to you how it works with an example of charge first. So we start from diffusion equation. But as we assume there's finite carrier density, and the long-range Coulomb interaction between charge will largely screen the fluctuation of charge density. So there's no time derivative term here. We just get this spatial divergence of the charge current. And the charge current is driven by gradient of the charge chemical potential. And plus, here's where the Langevin comes in, a white noise term. And then combining the two, we get a Langevin equation. And with the proper boundary condition, you can solve it. So you get a charge current fluctuating. And we know that charge current contribute to a magnetic field due to Biot-Savart law, or simply Ampere's law. And what we calculate is the spectral function at the site of the MV center of the magnetic noise of magnetic field fluctuation, and then Fourier transform to frequency space. So in the case of a charge, we'll get the familiar Johnson-Nyquist noise that is proportional to the conductivity, the charge conductivity. And you know that for a normal metal, the charge conductivity follows the Drude type of peak in frequency space. And for low frequency, it's mainly just a constant, so featureless constant. But for valley degree of freedom, the situation is different in 2 ways. One, there's no Coulomb screening because it's charge neutral. So we have the typical diffusion equation. There's time derivative and then relaxation term we consider in this model. And then the valley charge is proportional to a valley chemical potential. And again, the valley current is driven by the gradient of valley chemical potential. So here is the Langevin equation again. And the second difference is that valley current, as we've seen, is proportional to a spin density. So here it's generating magnetic field with the demagnetization, in the demagnetization way. So this is mainly the difference between the valley and charge. And then going to spin, so we have the same diffusion equation, but the main difference between valley and spin here is that the spin density is diffusing. So the spin density here is like a charge. The diffusing charge for the valley is a chemical potential, and the physical quantity that generates magnetic field is valley current. So there's this difference here. And due to these simple things, we get actually quite different spectral characters for valley and spin. And this is some quantitative prediction for the specific model I've shown. So the charge will contribute mostly a constant background, but the spin part goes down as frequency goes up in a way of omega -2 asymptotically. And then for the valley part, it goes up with frequency and approaches a constant with some parallel. So we imagine an experiment down in this way, like you just place the sender some distance away from the magnetic semimetal, make sure it's, the valley and spin are in the diffusive regime by controlling this distance. And then you can scan the frequency and get some spectral characters. So here, the NV is picking up 3 contributions at the same time. So it's a sum of them. And because spin contribution is dropping and valley is growing, so there's a dip here. And by changing this distance, this dip will shift. So this might be something to go after in an NV measurement. Okay, so okay, so I guess, let me say something to summarize. Magnetic noise can be a versatile tool to study low frequency transport in quantum materials, and the key point is to know how the transport degree of freedom will couple to a magnetic field. So in this simple model, the valley current generates a magnetic field in the demagnetization way, and for maybe other materials with other symmetries, you need to reconstruct this relationship, and maybe even from first principle calculations. So for the magnetic semimetal, we've seen that these 3 contributions can have different spectral characters, so frequency dependence, which might be useful to study their transport separately. And it might be interesting to also consider situations beyond the diffusive regime, like hydrodynamic regime, or to consider electron interactions, etc. Okay, thank you.